Okay. Um, let's see. Okay. Testing again. Okay. All right. So let's begin. Today we will initiate our study of recurrences. This is a machinery to analyze randomized algorithms, specifically running times of randomized algorithms. So rather than just jumping into recurrences, the way we will do is we will try to look at merge sort that we studied last time, that we went over the algorithm last time, and spend some time looking at how we would go about analyzing its running time. Then I will introduce another problem, which is called the selection problem, which is a very simple problem for which, again, there is a very interesting divide and conquer algorithm. We will look at ways to attack that problem, including a randomized algorithm, a probabilistic way of solving it. That will lead us to more recurrences, and that will set the stage for sort of the motivate why we need to study different kinds of recurrences, and we will go over that and spend this class and maybe part of next class going over how to solve recurrences. Okay, so recall we went over merge sort last time, and again I expect all of you to know it and have seen it before in some form or the other. I'm just reminding you, and I'm not going to write down the entire algorithm in detail. I'm just reminding you what its structure is. So at a high level, what's going on with merge sort is if you're given an array A of n elements, you first check if the array A has at most one element. If A has the size of A is less than or equal to 1, do nothing, return. Otherwise, merge sort left half merge sort right half, merge the two halves. Okay, that's the high level structure you should remember. Of course, we should be able to translate that into pseudocode that is more precise, and eventually translate that into real code. Okay, so that's the setup of merge sort, and whenever we look at an algorithmic problem, we will develop an algorithm, we will try to prove it's correct, and then we will analyze its running time. We already looked at its correctness, so let's try to understand what its running time is. Okay, so in general, just some rules of keeping track of running time. We will assume that basic operations, basic CPU operations individual CPU operations take unit time. Okay. Memory lookups take unit time. So multiplication, ifs and else, all these things take logical checks take unit time. Memory lookups take unit time. What we are interested in measuring is how does the running time behave as size of input grows. And in order to express this running time, we will often resort to asymptotic notation. Okay, so we will use our big O, big omega, big theta notation to try to reason about how this running time is. So, of course, this running time definition itself, we have to classify what it means. So, our emphasis in this class would be on the worst case performance of an algorithm. So, worst case running time. So, whenever you're asked, okay, analyze the running time of this algorithm, by default, unless there is something else that is stated, we'll assume that that's the worst case running time. Okay? What does worst case mean? Well, worst case means the running time. So we would say something like this. The running time of algorithm A is T of n if for all inputs, for all n, for all integers n greater than or equal to 1 or 0 or whatever, okay, the max over all inputs of size n, the maximum over all inputs of size n of running time of A on the input is T of n. Okay, we say the running time of A is T of n. What does it mean? For each n, if I look at all inputs of size n and look at the running time of that algorithm on each of those inputs and pick the largest, and that is my T of n. Okay? And in principle, I should really call it that's the worst case running time. Okay? What does it mean for input of size n? Well, think of it, to be really precise, we might have to say, okay, it's the number of bits in the input, but we will often clearly define what we mean by input of size n. Okay. It usually would be the number of words in the input. We will usually not go to the level of bits, we will go to the level of what is called words, but it will be very clear from the problem to problem what we mean by input. Any questions about this definition? Okay. Of course, that's not the only way to look at it. You could ask the question, best case input. Okay, we will almost never be interested in it because it's almost trivial to come up with an algorithm that has a very good best case running time. Okay. Best case is exactly the same thing, except you replace max by min. Why is it trivial to come up with an algorithm that has the best case running time? Good. That's a good way. Yeah.
If it's the best case, then you don't have to do anything to the set. So you just equals beginning. You don't have to do anything.
That's sort of right. So what you could do is your algorithm could do very well on one case and then ignore every other case. Okay, and that's trivial. And for most problems, if you have to do sorting, you would say, oh, I'm not going to do anything interesting when if the input is given in unsorted order. I'll just keep trying various things for the unsorted way. But when it's given in sorted order, I will just return it. So its best case running time would be probably awesome because it just looks at the input and returns it. So we would never be interested in this. Okay, it's natural. Another commonly used notion is average case running time. So instead of looking at maximum over inputs of size n, you could in fact ask something like, what is the average over inputs of size n? So you're replacing max by average. Okay? And that's a reasonable model, and it's used in many, many scenarios. There is a problem with this question when you're taking the average. One problem with taking the average is that you're assuming that each of these inputs is equally important or equally likely, right? And in practice, that may not be the case. Most often, we don't even exactly know what the input looks like, right? Now, you could replace the average by defining weights for different inputs and coming up with a distribution. So that's also considered average case, where instead of calling it the average of our inputs, you would say is the weighted average. Or it's an average according to some probability distribution. That's a common method that's often used. And it's very effective if you have a very good sense of what the input looks like in practice. If you know that the input always has this feature. For example, if you know that the set of things that need to be sorted are more or less sorted or have a certain property, then you can just focus your attention on that class of inputs. Okay? We will touch upon this average case at some points in the course, but for the vast majority of the class, we will focus on this. Okay? The worst case. Now, when we talk about worst case running time, we will so I'm now going to not mention worst case. So now you might say running time T of n equals order n squared. You might use that terminology now that we have the system information. What does that mean? Okay. Running time T of n is very well defined, right? What does it mean? It's among all inputs of size n. If I look at the worst case time taken over all inputs, that's what Tn is. If I say that that is equal to big O of n squared, what does that mean? Yeah.
Isn't that the order of n squared? That's the maximum amount of steps that typically are.
So the meaning of this is, since we are taking the max, that means for all inputs of size n, running time is less than or equal to Cn squared. Okay, so we have to be more precise. There exists a C and an n0 such that for all inputs of size n, running time of the algorithm is less than or equal to Cn squared as long as n is greater than. That's what the meaning of. Okay? Yeah.
I'm sorry. The end off there is that, and that's the maximum inputs. Can we not say something more than? Can we at least call that n max or something?
can you say that again?
Since we're looking at the worst case, we want the max set of inputs, so n would be n max for this algorithm, right?
No. Max is not on n. Max is max. So good. Thanks for the question. So max is the maximum of the running time. This is for all n.
Oh, that's right.
Okay. So for every n, so just literally imagine you write down all n from 1 till infinity. For each n, you look at all the inputs of size n, figure out which is the worst case for that algorithm. Then for n equal to 5, you do the same thing. N equal to 6, you do the same thing. That's how T of n is defined. And when we are saying that running time T of n is big O of n squared, that we are really saying that for once n is sufficiently large, n is greater than or equal to n0, from that point on, the running time is always less than or equal to Cn squared for every single input. So I should say right here. Yeah, for every input of size n, the running time is less than or equal to C. Okay? Okay. What is it when I say running time T of n equals omega n squared? What does that mean? Okay, so let's try to just follow this interpretation. What does it mean? So let's just write down here. There exists C and N0 such that max over all inputs of size n of T of n, sorry, yeah, running time of the algorithm on input, which is on the given input. Okay, so the maximum is over all inputs of size n. This is at least Cn squared if n is. So what does this mean? Okay.
Running time is at least n squared.
For what? Is it the case? So can I write the same thing? There exists Cn and 0 such that for all inputs of size n, running time is greater than or equal to Cn squared if n is greater than or equal to 1. What's the question?
At most.
Well, at most is big O. Already
Yeah,
said that.
at least.
Okay, so let me just write this down. So does this, so here is there exists C comma N0 such that for all inputs of size n, running time question, is this correct? Okay, why is it not?
Because it says max.
Well, no, it says max. The max cannot be replaced by min. You're right. If it was min, then this would have been correct. But this is max. What does that mean? If I'm saying that the maximum of a bunch of things is at least Cn squared, what does that mean? 1%. So let's say I give you maximum of a set of numbers is at least 25. What does that mean? Yeah.
The numbers, the rest of the numbers are less than 10.
No. No, all the numbers could be 90, then max is of course greater than or equal to 25. Again, if I say the max of a set of numbers is at least 25, what does that mean?
Max number will be more than 25.
Just 1%. Yeah,
Max number will be more than 25 or at least 25. Or
okay. Well, can you say it differently? So if I give you a maximum of a set of numbers that is at least 25, then you know that there exists one of the numbers in this list that's at least 25. Right? One of the things here is at least 25. So what we know is there exists here N0 such that for all n greater than or equal to N0, there exists some input of size n which the running time exceeds Cn squared. I've already included it in the other side, so I'm not going to. So this is critical. There exists some input of size n such that the running time exceeds Cn squared. Yes?
Can you explain the last part again?
So you're saying that, okay, there exists some constant C and some n0, so that if we focus our attention on n greater than or equal to n0, the maximum for inputs of size n is greater than or equal to Cn squared. What does it mean to say the maximum on inputs of size n is greater than or equal to Cn squared? That means that there is some input of size n for which the running time is greater than or equal to Cn squared. It doesn't mean that for each of them it's greater than or equal to Cn squared. Okay? So this statement is replaced by this. There exists some input of size n such that the running time of the algorithm on that input is greater than or equal to Cn. Okay? So if you're analyzing an algorithm and you want to argue that its running time is big O of n squared, you'll have to establish that after a certain point, once n goes certain or greater than or equal to some amount, every single input, it has to take time at most some constant time n squared. If you're trying to argue that the running time of an algorithm is omega n squared, what do you have to argue? That beyond a certain point, once n increases, beyond a certain point, for every n, you should be able to identify an input of that size for which the algorithm takes at least 3 times. Okay? So that is the, and in order to analyze our algorithm perfectly, we would like to prove both of these. We will have to give T of n equals big O and something, and T of n is big omega of something. So that way, we would show that for every input, our algorithm takes no more than this amount of time. And actually, there is some input for every n, for which it does take close to that amount of time. So then we will completely clarified it, right? That for every input, it is no more than 5 times n squared, but there is some input for which it takes at least 5 times of n squared or 3 times n squared and so on. Then we would have done our job. Okay? Good. So if you are able to prove, of course, T of n is big O of n squared and T of n is omega n squared, then you can now claim that T of n is theta n. Okay? Many times we might just stop and just prove this and not prove this, maybe because it's obvious, but ideally, whenever we are giving an algorithm, we should give both its upper bound and its lower bound. Yes?
Just for clarity, the sum input,
Yeah.
would that be just one out of many, or is that?
One out of many. So for example, in sorting, given n, how many different inputs of size n are there? N factorial. So you will have to, because of the fact that in sorting the numbers actually don't matter, it's just the order that matters. So there are n factorial different inputs of size n. So you have to demonstrate that one of those n factorial inputs, the algorithm takes so much time, okay, to prove an omega bound. Yes?
So what happens though, could that be misleading if there's, for instance, an outlier?
Yes, absolutely. But remember, all those objections should have come when we were talking here. Once we have agreed on worst case, this is what we have to do. Okay? But you're absolutely right. And there are certain models that have been looked at more recently where you argue, oh, my algorithm actually works well for everything but for these handful of problems. And those are somewhat more rare scenarios, because often when an algorithm doesn't work well on some things, you can actually find many situations where it doesn't work well. But yes, here the outliers are treated the same way as in the core. Okay? Any other questions? Yes?
When we say that it's greater than or equal to C of n squared,
Yeah.
shouldn't we mean that any input should be at least C of n squared?
No. When it's greater than or equal to C of n squared, we mean saying that there is some input of size n for which your algorithm takes a lot of time. For many other inputs, it might be running fast. But there happens to be some input for which it takes a lot of time. And since we are focusing on the worst case, that's what decides what its time is. Okay, so you might have an algorithm that works very well on a large class of inputs, but then some inputs it just seems to struggle and take a lot of time. From our purposes, the running time of the algorithm is completely determined by those worst case inputs. Again, because we are focusing on worst case. Okay, all right. So let's go ahead and study our merge sort procedure. Okay. So the so let's study our merge sort procedure. Last time when we analyzed merge sort or tried to understand about merge sort, it was very clear that the only interesting thing that was going on was in the merging, right? Okay, and we figured out how merging also works. So before we get into merge sort, let's try to understand the running time of merging. Okay. So how does merging work? We had two arrays and we tried to figure out. So we have two arrays. And we merged the elements in those arrays into this, okay, into this larger array. So we kept a pointer here, we did a comparison, and we moved a pointer here. So one by one we did that. So if you had m elements in this array and k elements in this array, so that this array is of size m plus k. Okay, how many operations does it take to do the merge? It's m plus k times something, okay, but because for each check you're spending some amount of time, it takes some time to copy and so on. But again, we are actually, since we are happy with the big O notation, we are not going to worry too much about those specific details. And I want to emphasize that we also cannot be very specific about those kind of details unless you exactly tell me how much does a copy cost, how much does an addition cost, and so on. So we will just count them all as one, okay, and we'll be very liberal with our choices. So here we will say the running time of merge, and I'm going to even write this out as simply as m plus k. I'm not even counting those. I'm not saying it's 2m plus k, 3m plus k, and so on. Sometimes I might put their numbers, sometimes I won't, but we don't have to worry about it because eventually we're going to cast everything in a big O notation. Okay, so notice that the running time of merge is actually independent of the input. For all inputs, m and k, it will basically take m plus k. Okay, because it's going to look at each of these elements and it's going to compare and it's going to move down. Okay, it's possible that there might be fewer comparisons needed. For example, if let's say all these elements are smaller than this element, then you might just copy all these elements first. But then you don't have to do any more comparisons. You might just copy that without doing any comparisons and so on. But as far as if you ignore the constants, the running time of the merge is worst case running time is always m plus k. So you can say here that the running time of merge for merging m with k is theta m plus k. Okay. In the algorithm, m and k are about the same, right? In merge sort, because so if both of them were about m, then the running time is nothing but. Okay. All right. So let's do the following. So let's try to understand what is going on. So let TFN be worst case. Okay, I'm not going to use the term worst case. Let TFN be running time of merge sort. Okay? So let TFN be the running time of merge sort on an input of size n. So what is going on? You are, so let's look at the first step where it says array is size less than or equal to n. So T of 1 is simply 1. If your array is of size 1, you just return it. So let's count that as just 1. If your array is of size n, then you first sort the left half. So in the worst case, if my input is of size n, my left half could be worst case possibly. So I'm going to write, let me say that's the worst case. That's the left half. I think, let me use floor. Then we sort the right half, which is the ceiling, plus the time it takes to merge two arrays of size n over 2. And we have figured that out. It's theta of n. Okay, I'm going to just write it out as n. Okay, it turns out whether we put 2 times n, 3 times n, 4 times n, it's not going to matter in terms of the theta notation. Okay. Is that clear? So that is the running time, the worst case running time for merge sort. Notice that we have no less than equal to or greater than equal to, because for merge sort it turns out for every input it basically takes the same amount of time. It doesn't do some inputs faster than the others. But there are many, many other algorithms that actually differentiate, but merge sort does not. It just takes the same. You merge sort this, and okay. Okay. So let's try to understand this. So the first thing you notice here is this n is always an integer. We talked about our asymptotic notation. We didn't care about whether n was an integer. We just viewed them as functions and so on. And for the most part, we will keep sort of shuttling between these two situations. We will, whenever it's very useful, we will assume n is an integer, but many other times it's not necessary. If you're looking about growth of functions, we can smoothly view n as increasing all the time. But for a recurrence, of course, this is important that we have this notion of n being an integer. We are not talking about arrays of size 5.3 or 5.4. Okay, so this is our recurrence. So you first you should understand, so this is n greater than 1. You should understand that in principle, if I asked you what is t of 10, you can go ahead and compute it. Do you see that? What is t of 10? T of 5 plus t of 5 plus 10. What is t of 5? T of 3 plus t of 2 plus 5. What is t of 3? We can go ahead and compute it, so we can keep doing this. And at some point we will end up with t of 1, and we will replace that by 1, and we can do it. So this is a complete blueprint for calculating t of n for every n. So it completely specifies what's going on. But of course, we don't want to do that. We want to see how does t of n grow with n. So this is exactly what is called a recurrence. So let's just quickly see how we would go about solving it. Okay, so let me just write that out here. T of n equals t of n over 2 plus t of n over 2. Okay? We are going to solve it in two different ways. And then we will introduce other recurrences, and we will see many other ways of solving it. So the first thing we will do here is, and we will do this many times in this course, is we will ignore the floors and ceilings. Okay? In general, we have to be very careful about it, and we should make sure we handle it. But for many, many times, as far as growth of functions goes, it doesn't matter. Okay? So we will make assumptions along the way. So this is not a complete precise argument, but it will capture the gist of what's going on. So I'm going to replace that. Remember, there is always a base case, T of 1 equals 1, and T of n equals 2t n over 2. Okay. One other way of justifying this is to say that what is going on here? Every time n is being divided by 2, right? And so on. And the worry is maybe if n is odd, what happens? Right? So you could say, oh, I can assume that n is even. Does that solve the problem? No. Because maybe in the next round when you're doing this again, n is odd. Right? When you do the recursion. So the one way to address this, oh, I'm going to assume that n is the power of 2. You agree that if n is the power of 2, we would never have this problem of floor and ceiling. If you keep dividing by 2, you always get some n power of 2, and then power of 2, and power of 2, and so on. So one other way of justifying this is let me assume n is the power of 2. Okay, if n was not a power of 2, I can of course add some, I can pad the input with certain numbers and make it a power of 2. Okay, so that's another way to justify it, but for now let's not get into too much of the justification. Let's just focus on this recurrence. T of 1 is 1, T of n is 2t n over 2 plus n. This is n plus n. Okay, so what we will do is we will follow a method which is called the iteration method, and it's nothing but just you just look at the recurrence and just try to unravel it. It's also sometimes called the recursion tree approach, and I'm going to, which is the same as the recursion tree approach. Okay, so let me present it as an iteration method first. So it's straightforward. T of n equals 2t n over 2 plus n. So what we do is we start from T of n equals n plus 2 of t n over 2. Okay, and I'm going to apply recursively this. So sometimes it's helpful, since we are using the same n again and again, sometimes it's helpful to use a different variable for n. So it's sometimes helpful to write it like this. T of box, instead of n, I will just replace it by box. So T of box is 2t box over 2 plus box. Okay, this is my pattern that I want to capture repeatedly. So T of n is n plus 2t n over 2. So this is n plus 2 of n over 2 is box. So it becomes 2t of n over 4 plus n over 2. N and n add up to 2n. So I get 2n plus 2t n over 4. Okay? Again, I apply that T of n over 4 is equals to, I replace box by n over 4. So I get 2n plus 2t 2 times 2t n over 8 plus n over 4. I made a mistake.
4t n over 4.
Okay, so I get another n from this, and I get 3n plus 8t n over 8. Okay, so at this point, of course you can keep on going, but then your job is to identify what kind of pattern are we getting here. Okay, so let's try to see what's going on every time you go. So you know the next step will be 4n plus 16t n over 16. Okay, and we are not ever going to worry about floors and ceilings because we are assuming that n is the power of 2, so everything is going very clean. Okay, so what do I write this out? So every time I'm going, so what happens after when I'm at the ith step here? Well, I'm at the ith step here, so I would say I times n plus 2 raised to I t of n over. That's the general. And once you've identified this pattern, I claim we are done. Yes?
Isn't the first part n log n?
Which part?
The first n part, n, 2n, 3n, 4n, isn't that just n log n?
It will become n log n. Yes, we are going to derive it. Absolutely. I'm going to try to explain why is it n log n. So we are increasing by, we are adding n, and so on, and we get this. Good. So this is clear. Okay. Now the question is, how long does I go? So what is I? At what point do I keep on going? Why don't I just keep on going with this? Well, remember our base case is 1. You don't apply the recursion to t of 1. You have to stop at t of 1. Okay, otherwise it will keep on going. So we don't apply the recursion to t of 1. So we stop at the point where n over 2 to the I is 1. So what is the stopping criteria? N over 2 to the I is 1. So 2 to the I is n. So I equals log n, log base 2 of n. Here bases are important, okay, because the specific value of I might be important. So this is log base 2. Okay, if I don't put anything here, this is log base 2. So now I get t of n. Notice that this statement was true for every I, right? It was true for 2, for 3, for 4. So it's also true for I equals log n. So I put n times log n plus, this is 2 to the n times t of 2 to the log n times t of 1, which is n, times t of 1, which is 1. Okay? All right? Now, once you have this, notice that this was true for every single input, right? So you can, at this point, you can claim, you agree that this is greater than equal to n log n, okay? And it's less than equal to 2n log n. Why is less than equal to 2n log n? Well, n is of course less than equal to n log n. So this implies that t of n is theta of n. Okay, so we have established that the worst case running time of Mozart is theta of n log n. Okay? And how did you do that? Well, we wrote this recurrence down, and we solve this recurrence by this iteration method. Okay? Okay, so I'm going to, for completeness, I'm going to show you a second method of proving the same thing. Okay, so okay, let's go back to our original recurrence where we had the floors and ceilings. Let's say I insist that you do not make any assumptions about the floor and ceiling. That you have to, you cannot remove these floors and ceilings. You have to look at the performance of this particular algorithm, and n could be odd. I don't know. Okay, so one way to do this then is, I think it's almost impossible to try to do it with the iteration method, because imagine taking the floor of n over 2 and so on. It's just not going to work. But the one way to attack this is to do it without the floors and ceilings, and now you have a very good guess. And what's your guess? the T of n is theta of n log n. So now we're going to try to prove this. Okay? We will prove the following, and I'm going to prove one part, the other part is similar. So we're going to prove that for all n, let's say all n greater than or equal to 1, T of n is less than or equal to 2 times okay? We're going to prove that. Now, what will happen is sometimes instead of proving that, let us not commit ourselves to a constant. Let's just say that we're going to prove that T of n is less than or equal to C times n log n. And we will choose our C. We might need to choose our C at the right time, but let's leave it like that. Okay? You agree that if I prove this, and you can also play around with this 1 instead of 1, you could put n0, but doesn't matter. You agree that if you prove this, that would imply that T of n is big O of n log n. Okay. So how are we going to prove this? We have no other machinery other than to use induction. Because we have to prove this for every single integer. And we are given the recurrence, just like sort of in Fibonacci sequence, we knew what the recurrence was. Here we are given this recurrence. The question?
Yeah, sir, so if we take n equal to 1
Yeah.
and put it in that formula of T of n, it comes to be 0.
Excellent.
Yeah,
Good. So let's try to prove this by induction. And we'll enter a problem with the very first situation, which is the base case. So base case, we say n equals 1, and T of 1 is 1, C n log n is 0. Gone. So our proof failed in the very first step. Okay? So what do we do? Well, one option, there are multiple ways to try to fix it. One option is what? I say, okay, I'm just going to prove this for n greater than or equal to 2. And remember that for the big O notation, I don't really need to fixate myself on a particular starting point. Okay? So this is what I'm going to prove. So what's my base case then? 2. So base case is n equals 2. So if n equals 2, what is T of 2? What is T of 2? 2 times T of 1 plus 1 plus 2, sorry. Okay, so that's equal to 4. What is C n log n? Is equal to 2C. So this statement would be true as long as C is larger than or equal to 2. Okay, so I'm not going to commit my C yet. But you agree that as long as my C is bigger than or equal to 2, T of 2 would be less than or equal to 4. Would be less than or equal to C n log n. Okay? So one condition I get from this, the C is greater than or equal to 2. Very, very critical thing to keep in mind, and I think many of you understood this while you're discussing asymptotic notation and so on. The C has to be fixed. You cannot choose one C for one n and a different C for different n. It's very important. In the same way, in the induction proof, you cannot keep changing your C in the middle. So that's why I don't want to commit to my C. I just want to make sure that we will choose a C that satisfies every condition that we place. Okay? Okay, so now we do the induction step. What's the induction step? T of n. We are choosing n to be greater than 2. T of n equals T of ceiling of n over 2 plus T of floor of n over 2. And plus n. What do we know about T of ceiling? You agree that if n is bigger than 2, then floor of n over 2 is less than n. Ceiling of n over 2 is also less than n. So we are going to apply the strong induction. That is, the statement is true for everything less than. Okay. assume statement true. Assume T of m is less than equal to Cm log m for all m less than. Okay, we will all assume that. And now we're going to prove it. So T of n over 2 plus T of ceiling plus T of floor plus n. What is the T of ceiling? N over 2 is that we know is less than equal to m over 2 log m over 2 plus sorry, why am I using m? N. Plus n. Oh, I missed the C. Okay? Everybody happy so far? Okay. So now what do? We want to prove that this is less than or equal to C n log n. Okay? That's our goal. Just let's keep that in mind. Less than or equal to C n log n. Okay? If the floors and ceilings were not there, okay, if the floors and ceilings were not there, let's just do a quick calculation. If the floors and ceilings were not there, what would this look like? 2C n over 2 log of n over 2. You agree? Floors and ceilings were not there, this is what it would look like. Well, this would cancel with this. So it will be Cn log of n over 2. What is this equal to? Oh yeah, plus n. Well, what would this be? This would be Cn log n minus Cn log 2, which is 1, plus n. And we wanted to show that this is less than or equal to Cn log n, so this statement would be true as long as C is bigger than, well, in this case, C is bigger than 1, right? Okay, so there is room to play with. So what we're going to do is, that suggests that we have some room to play with as far as C is concerned. So we're going to essentially do the same thing, except that we cannot remove the floors and ceilings. So let's do the following. Let's say that this is, so here is the first attempt. Let's do the first attempt. So C times. Okay, so one problem I have in you have the ceiling of n over 2 plus floor of n over 2. What is that equal to? N. So I can add these two. That's nice. Except that these two quantities are different. Okay. Okay. So, and this is a little bit of a real pain to look at. This is n over 2 and ceiling and n over 2 floor. What if I simply say that, oh, that's less than or equal to n? You agree? Ceiling of n over 2 is less than or equal to n. So I get log n plus C of floor n over 2 log n. Okay. What is the sum of these two? Cn log n plus n. Do I get what I want? No. At this point, you can't say that, oh, this is just big O notation, so this and this are the same big O. No. We are proving something by induction, so we have to follow through and everything. So it turns out that this is too much of a weak assumption. So let's go back. I'm going to erase this. What if I try to do something else? If I do if I replace this by n over 2, then what will we get? Then I will get exactly what I got there. Okay, you can add these two, so you'll get Cn log of n over 2, and you'll get it what you want. But it's not correct to replace by n over 2. You agree? Why is this wrong? I can't go from here to here. Why is this?
Because if the floor is smaller than n over 2.
Because the ceiling of n over 2 is bigger than n, could be bigger than n over 2. So this is completely not allowed. Okay? So what do we do here to fix this? So there are a number of things you could do. You could say, oh, the ceiling of n over 2 is no more than n over 2 plus 1. Except that the problem is if you have a log of something plus 1, it's very difficult to manipulate. So we're going to be a little bit more crude about our approximation. You're going to say, let's look at the ceiling of n over 2. I'm going to claim that ceiling of n over 2 is less than equal to 3n over 4. Okay? For n sufficiently large. So when does ceiling of n over 2 become big, smaller than n over? So if n was 2, actually this is true every time, right? So ceiling of n over 2 is, if n is 1, this may not be true.
Because you can cancel out. If you just do n over 2.
Plus 1. So no, so let's try, just play around with some examples. So if n equals 1, this is not true, right? If n equals 1, what is the ceiling of n over 2? 1. What is this? Is 3 over 4. 1 is not less than equal to 1. But if n is 2, this is 1. This is above 1. If n is 3, this is 2. And this is also over 2 and so on. I think you can check it and you can verify it, also prove it, that this is always true. So the advantage of doing this is I'm going to get this to be 3n over 4, 3n over 4 plus n. What do we get here? So C log 3n over 4 is common. Ceiling of n over 2 plus floor of n over 2 is n plus n. What is this? Cn log n minus, or let me write it as plus C log 3 over 4 plus 1 times n. Okay, I don't know whether it's very clear to everybody. So all I did was log of n, 3n over 4 times 3n over 4, log of 3n over 4, I split it as log n and log 3 over 4, and I get like this. Now, is this less than or equal to C of n log n? Okay, this is the same as this. In order for this to be less than or equal to C n log n, what do we want this to be? Less than? Equal to? 0. You want C of log of 3 over 4 plus 1 to be less than or equal to 0. So let me write that down here. What do we want? C of log of 3 over 4 plus 1 to be less than or equal to 0. What is log of 3 over 4? Is that positive or negative? Negative. So this you can always set your C so that C times log of 3 over 4 plus 1 is less than or equal to 0. In principle, you can set your C to be at least, I move it, so this is the same as C a log of 4 over 3 should be greater than or equal to 1. So C should be greater than or equal to 1 over log of C should be greater than or equal to 1 over log of 4 over 3. So everything here is true as long as c is greater than or equal to 2 and c is greater than or equal to 1 over log of 4 over 3. So what do? You set c to be the bigger of the two. And then every statement here will be true. Okay?
So in this case, you said C, but you posted max of either 2 or 1 over log.
Yes. And I think we can determine that. What is log of 4 over 3? So 2 to the power of what is, so this is,
1 over 1 over.
so this is
minus
greater
1,
than,
right?
so square root of 2 is about 1.4. So this is less, so this is actually the bigger quantity error. This is bigger than 2, I think. But you can calculate.
Log of O minus log of 3 is 2 minus log of 3.
Correct. Yeah.
Right?
So it is 1 by some number smaller than 2. Oh,
No, I think 2 is bigger.
2 is bigger. Okay. All right. Okay. Possibly, yeah. Yeah.
Because 2 minus log of 3 is usually
No.
smaller than 1. Smaller than 2. No.
I think
Smaller
it
than
depends upon what the power is. Okay, so if we can compare whatever these two, whichever the smaller one, the larger one, we'll take it. So that is really the bona fide proof for this, that this is big O of n log n. You can also prove omega of n log n in the same way. Omega of n log n will likely be easier, but you can apply the same method to prove omega of n log n. Okay, so but this is a good way to know it. Often we won't require this way to do it because it turns out that floors and ceilings can be ignored in all of these situations. You can just use the other method to do it, but it's very good to know that if you are required to do it this way, then you can do it. The reason we are always comfortable ignoring floors and ceilings because we know that in the back of our mind, we know that this is one way we can go about it. Okay, so we're going to look at a lot more recurrences. This is one of the most simplest recurrences we can think of. Then we're going to hit a number of other recurrences. Let's motivate a few others. So at this point, one thing we would want to do before we go and study a lot more algorithms is to understand what other kind of recurrences that will come up. Okay, so but I think rather than going and listing you techniques to solve recurrences, I'm going to introduce a few more problems and a few more examples to motivate why we might need other kinds of recurrences to solve these problems. So one very simple problem that very similar to sorting is that of selection. Selection is finding an element of a certain rank in an unsorted list. Okay? So a very classic problem that you do it again, it comes up again and again in various applications, is finding the median. Okay, in statistics, you often want to study the median performance, the median behavior, the median salary, the median age, and so on. So what is the median? Median is if you have a list of n elements or n numbers. Median is element of rank n over 2, exactly the halfway point. Okay? And again, you have to be very careful. If n is odd, what do? You can come up with any rule. You can say it's the floor n over 2. Well, it's the element of rank n over 2 once you sort the list. Yes. When I say rank, it automatically means that it's its position. Okay. You could define this as the floor. You could also define it as the ceiling, and some places they define it as the average of the two, and so on. It doesn't matter. Let's just focus on one or the other. Let's just assume it's the floor. Okay. All right. So that's the general problem. Okay. And we're going to study some really nice algorithms for this, and at least one of it, many of you may not have seen. But before we do that, let's try to see how could we go about doing finding the median. Let's say we're interested in finding the median. So let's before this, let me ask you an even simpler question. Let's say I give you. You agree that if the list was already sorted, can you do the selection problem trivially? You just have to look at one position. Okay? So sorted means selection is trivial. Okay? You often also get a question of the following form. You could say you might be given a sorted list, and you're also given an element x, and you're asked to find the rank of x in the sorted list. Okay, you're given a sorted list, and I give you an element x, and I want you to find the rank of x in the sorted list. How do you do that? You would do binary search. Okay, and I'm not going to go over it. People should know how binary search works. You compare it with the middle element, and if it is bigger, you look on the right hand side. If it's smaller, then look on the left. Repeat. Eventually, you will find the index. If it belongs to the list, you will find the index where it lies. If it does not belong to the list, then you will find the two indices where it should have been. Okay. Now, binary search itself takes log n time, because every time you're dividing by a factor of 2. So you should remember this, that binary search takes time, theta log n, if the list is of size n. Once the list is already there, binary search just takes theta. Okay. There is a recurrence for that also you can write. I will let you folks work on it. Okay, so let's try to solve the selection problem. So any suggestions for how to solve the selection problem? So I want you to find the median of a given list. What do you do? Yeah?
Can I just sort it and then binary search?
Good. So, well, no. Then you don't need to binary search. Once you sort it, if your element, you just have to look it up. Yeah. So you could just sort and return. So sort A, if A is a list, sort A, return AK, or A median. Okay, the median position. What's the running time of that? Theta of n log. Okay. Let's say instead of the median, I asked you to find the minimum. What would you do? Sort and return the first element, but can you do faster than that?
It's just linear. Pick one and then compare.
So you just start from some place, and then you start from the beginning, store the minimum, keep running through the array, linear scan. Okay, so minimum takes clearly theta n, maximum takes theta n. Agree? What about second minimum? Why? You will do one round and then you will do another round. Okay? So the question is, okay, second minimum, third minimum, and all, you can do that. What about median? And certainly you can do it in n log n time. But the question is really, I'm just finding just one element of a certain rank. In order to find that, do I have to sort the whole thing? Is the question.
Essentially, you just need the first one.
Well, in some sense, you just need to the first half, but you need to know that everything in the second half is bigger than the first half and things like that. Okay. Let's see. People have some thoughts. Yeah.
I just thought if you said that you can find the second minimum,
Yeah.
third minimum linear time,
Yeah.
then just find the midpoint of the length and then do that incrementally until you
But you need to find the n over 2 of them, and that will take you quadratic time, which would be even worse than just sorting the whole list. Okay. Yes.
Can we use the big selection?
You can try to do that. Go ahead.
Yeah.
So what would you do?
We can pick so for the step 1, we can pick a keywords.
Okay.
And then we can partition the whole array into 2 parts.
Okay. Okay. So the suggestion is the following: you can take this array. You're given an array, and you pick an element. So let's just take the first element, for example, and you partition the element, and this is what it's referring to as pivot. So you partition the array around the pivot. What does it mean? I'm going to split the array into 2 parts. One part there will be one position where it's x. Everything here would be less than x. Everything here would be okay. Let's assume, by the way, for the purposes of our discussion, all the elements are distinct. Okay, so we are not going to worry about equality and so on. Okay, how long does it take to go from here to here? How would you go from here to here? Yeah? Did you have something? Any? Okay, how do you do that? Yeah, so just walk through this, and you can do it smartly. You can just walk through this. If it is less than x, you can put it here. If it is greater than x, you can put it at the end, and you can keep filling it like this. Okay? So, and then finally there will be a spot for x, and you put it there. Okay? So partitioning takes time. So far, so good. Yes?
So I assume that by partitioning, you can split it into 2, and then you can look at each set.
Yeah.
And depending on where the pivot is, to determine which half you look in for the median.
Yes.
However, if you pick a really bad pivot,
Yes.
you're gonna have, like, say, 1 and n minus 2
Yes.
in the other one.
Yes, that's true. That's absolutely true. So let's do it systematically. So here we have this. So first thing to observe is, okay, so what do we do after this? So what was I looking for? I was looking for the median. So what do I do? Everything here is less, everything here is greater than. So if x was, let's say, at 25th percentile, then where is the median located? On the right. Is that element the median of the right? No. So in fact, the recursive problem we are solving is not a median problem. It could be a problem of looking for the 25th position, or God knows what. So that's one thing to understand. When you try to solve the median problem recursively, the recursive problems you are solving are no longer median. So then you should ask your question, should I really be solving the median problem? Why don't I solve the general selection problem? The general selection problem is, I give you an array and I give you a k, and I want you to find the element of rank k. because if in your recursion you're finding that you have to solve that, then you might as well start by solving the general problem. And in order to solve the median, what do you do? Once you have written the code for this, you just invoke select AK with k equals n over 2, the median position. So let's forget about the median problem. Let's focus our attention on this problem, that of what I've called here selection. Find an element of rank k in an assortment. Okay, so let's do that. So what's our step? First step, partition the array around, let's say, the first element. Okay, so let's say x is just the first element. Partition array around the first element. Okay, now what do? You want to make a recursive call. Okay, so let's say the position of x here is I. Suppose I equals position of x after the partition, okay, in the array. What do you do now?
I is less than k.
If so, let's consider that. There are three cases. What's the easiest case? If I equals k, then we are done. We are very lucky. The pivot that we started off with turned out to be exactly the element we were looking for. So you return. What do you return? X. X is the value, right? So you return X. If I is less than k, what do?
You search the right half.
Okay, you search on the right hand side. So let's call this AL, let's call this AR. Or actually I can be more precise. So you're going to search in the array AI plus 1 through n. So you select A in the array I plus 1 through n. What element are you looking for there? You're looking for k minus I. If I is greater than or equal to k, what do? You select A 1 through I minus 1. What position are you looking for there?
I minus k.
What position are you looking for? If you're looking for the first,
Oh, k.
it's just k.
It's just k.
This is the perfectly good algorithm, and this is, those of you who are familiar with quicksort, it's a little bit like quicksort, except that in a sorting procedure, we are sorting both sides. Here we don't need to. So this is where we are hoping we are making a lot of savings. That if you're looking for an element of a certain rank, we have to just look for where that element could be belonging. Okay? All right. So now let's try to analyze the running time of that algorithm. So okay, so what do we do here? We have to analyze the running time of the algorithm, and again we are interested in the worst case running time of the algorithm. So we let's say we are looking for the kth element. We are looking for the element of rank k. So there is some amount of time it takes for us to do the partitioning. That always takes linear time. So we know that. After that, we are only going to call either one of the two selects. We are not going to call both. Okay? So my recurrence looks like something like this. T of n is less than equal to the time it takes to do the partition. And by the way, I forgot to put a base case. I should have put a base case that if there is only one element in the array, then you can simply take care of it. But okay, T of n is less than equal to n. But then what happens? Either I look in the left side or I look on the right side. If I look at the left side, what's my running time? T of? Well, it depends on the size of the left hand side. What is the size of the left hand side? I minus 1. If it's the right hand side, what's the? It's n minus I plus 1 or something like that. But I don't know which of these two it will take. I have no idea. But I'm assuming worst case, so I should sort of assume that it's going to be the larger of the two. Okay? So it's sort of like the maximum of these two quantities. I'm still being a little informal, so it's the maximum of these two quantities. Or I could say it's the maximum of T of the maximum of either I minus 1 or n minus 1. But as was mentioned, that you could choose your, you could set it up so that the left side, one of the sides is just all the elements, n minus 1. You could set it up so that one of the sides is all the elements. If that was the case, then I would be, let's say I was 1, so that the first element that you looked turned out to be just the first element and everybody else was greater than that. So you're searching in the remaining n minus 1, then you're searching in the remaining n minus 2 and so on. So then if that happens, this recurrence will look like T of n is less than equal to n plus T of n minus 1. Okay? And now if you know your iteration method, you can really solve this very easily. It's in fact a simpler recurrence than the merge sort recurrence. Why is that? Well, I can write this box out. T of box n is less than equal to box plus T of box minus 1. So I could just repeatedly apply this rule. So I get less than equal to n plus n minus 1. Next I will get n minus 2. Next I will get n minus 3. So on, and I'll end at T of 1, which will be 1. So I basically get n plus n minus 1 dot 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 dot. So this is nothing but an arithmetic series, which you should remember is n times n plus 1 by 2. Okay, the sum of first n numbers is n times n plus 2. Well, so that means what is this? If in a big O notation, if you have to make it the simplest possible thing, this turns out to be T of n equals big O of n squared. And in fact, this is tight. There is an input, right? We really did identify this input where I give you a sorted input and you are repeatedly taking time to, and let's say I give you a sorted input and let's say I want to find the largest element or something like that. Then I first, on the first, I look at n minus 1, then I look at n minus 2, then I look at n minus 2. Okay. Okay, so much so so we could have as well sorted the whole list in the first place. Because remember, n log n is smaller than n squared. Much, much, much smaller than n squared. Okay, again, why is that? You have n log n versus n squared. So the thing you're comparing is log n versus n because there is an n in both places. Log n grows very, very, very slowly. N grows very rapidly compared to log n. So this is much faster than this. Rather, the algorithm running in this time is much faster than this. This function is much slower than this. Okay, is that clear? Okay, so this is the worst case performance of that select algorithm. So how would you try to, there are some good properties of that algorithm, but somehow they are not coming up in this analysis. Okay, this assumption of worst case is really making some of the problems that we're facing. So what would have helped? How could you modify that algorithm to make it work better? Certainly in the worst case, that's a bad algorithm. What could you have done in the algorithm to make it better? Yeah. Selecting a proper pivot. But you don't want to spend too much time selecting a proper pivot, so you want to do it something quick. So you would select, let's say, a random position in the array and make that as your pivot. Okay? So choose your x at random. But let's do exactly the same thing. Choose your x at random, let's do exactly the same thing. Okay? So so this is called random select. Choose index j at random, uniformly at random, and then set x equals aj, and now do exactly the same thing. Okay? Let's try to understand that a little better. So, what do you think now will happen? So, if I could still be supremely unlucky, and I could have a split of 1n minus 1, or 1n and minus 2. Let's ignore you can put x along with one of the two. Okay, so that. Okay, let's leave it like this. 1n and minus 2. We could be supremely unlucky and we could do 1n and minus 2. We could be supremely lucky and we could do n over 2, n over 2. That will be great. Or we could be somewhere in the middle. Okay. So let's try to understand where we are going with this. So let's say let's look at the different possible splits. Okay. So left half and right half. And okay, let me actually it's more convenient to split them so that they add up to n. So let me leave it like this. So you could have a split of 1 and n minus 1. You could have a split of 2 and n minus 2. You could have a split of 3 and n minus 3. You could have a split of 4 and minus 4. N minus 1. Okay? I'm including my x to either left or the right. You agree that all of these are possible. Okay? And what is the likelihood of each of these? Equal, because I just picked a random position. So each of these is equally likely. So 1 over n minus 1, it will be, and yeah, so there is green. So yeah, so I have this. Each of these is equally likely, and I don't know. My k is arbitrary. K is not chosen at random, so my k is arbitrary. So I don't know which side I would go at. I could go here, I could go here, and so on. But let me assume the worst case. So let me assume that. Let's look at the max of the two. N minus 1, n minus 2, n minus 3, n minus 4. Then I go to n over 2. Okay, notice that I'm ignoring this floor and ceiling here. then I go back to maybe 2 plus 1. Okay. All right. So what can I say about, so I can say something like this, that with 1 over n minus 1 probability, okay, actually to be really precise, what's going on is, with 1 over n probability, I have found the element that I wanted, and the rest of each of these appears with probability 1 over n. So with probability 1 over n, rank, I might split it as n minus 1. I might be searching, my recursion is on n minus 1. With probability 1 over n, my recursion is on n minus 2. With probability 1 over n, my recursion is on n minus 3. With probability 1 over n, my recursion is on n over 2. And then it goes back. With probability 1 over n, my recursion is on n over 2 plus 1. Probability 1 over n, my recursion on n over 2 plus 2, and so on. And with probability 1 over n, my recursion is n minus 1. Okay. So if I'm assuming that in the worst case I'm always looking at the larger of the two halves, what I find is the probability that I'm looking at a selection, my recursion is going to a set of size n minus 1 is 2 over n. N minus 2 is 2 over n, n minus 3 is 2 over n, n over 2 is 2 over n. Okay? Probability, recursive step is on array of size, let's say I, which is greater than or equal to n over 2, is equal to. Okay, so that's what's going on. All right, so rather than trying to analyze this, let me ask the following question. What is the what is the expected size of the larger half? What is the expected size of the larger half? Of the larger half. What is that? The larger half will always be bigger than equal to n by 2.
N minus n divided.
No?
3n over 4.
3n over 4. Because basically the larger half could be any number between n over 2 and n. All equally likely. So the expected size would be, of the larger half would be 3n over 4. Okay. If we are supremely unlucky, we will be in the situation where the larger half is n minus 1. Okay. If we are lucky that we are doing the recursion always, but we are lucky everything will split nicely, evenly, then we will just get n over 2. But on average, it will be somewhere in the middle. So it will look like this. Okay. For now, let's assume we have the following recurrence where every time we get this expected behavior. So if we get, this is not at all a valid analysis, but let's suppose if our behavior is expected in every step, in every recursion, what's going on? Then what kind of recursion would I get? T of n is less than or equal to, remember I'm doing a partition which is n, but then my remaining problem is 3n over 4. This is the recurrence we have not seen before. N is less than or equal to n plus t of n over 4. Okay, this is assuming I'm always doing this expected behavior. I mean, that's not a valid analysis in any way, but let's assume that. So it will be good to understand what this recursion comes out to. Okay, I will let you try to analyze this using the same iterative method that we have done applied in all situations. And you should be able to prove it by taking advantage of understanding geometric series. You should be able to prove that this is big O of n. And this is what suggests that this algorithm is actually a good one, because it will tend, we'll argue later on that this will tend to have this nice behavior, so that its performance with very good probability will be big O. Okay? Alright, I think I'll stop now, and we will cover this and do more recurrences next class. Let's stop here 1 second.